Ever been sipping a drink through a straw and just kind of marveled at how the liquid climbs up?
Yeah, or maybe listen to a really perfectly strummed guitar note.
Exactly. And wondered why it sounds so clean, so pure.
Well, these everyday things, they aren't magic, are they? It's physics.
Right. And today we're actually going to explore some of these surprisingly insightful explanations tucked away right here in this book.
That's right. We've got Physics Old is Gold Solution, graded 7, 2079.
Quite title.
It is. Think of it like a concentrated dose of physics problem solving. It's aimed at the grade 12 curriculum over in Nepal.
Oh, okay.
Yeah, you can see the cover here as Mita's book publishers. The author is Dharm Bahadur Rokhaya.
In the year 2079.
Yeah, 2079 Vikram Samvat. That translates to around 2022 or 2023 for most of us using the Gregorian calendar.
Gotcha. So our mission today, for you listening, is basically to skip the really heavy calculations.
Definitely no complex math today.
Right. And dive straight into the core ideas, those kind of aha moments,
The concepts that help you understand how the world around you actually ticks.
Yeah, think of this as your shortcut to grasping some fundamental physics without needing a PhD overnight.
So looking at the contents page here, you really get a sense of the scope. It starts with mechanics.
Okay, mechanics. That's like motion, forces, how things move.
Pretty much, yeah. The nuts and bolts, then it goes into heat and thermodynamics.
Energy, temperature, that sort of thing.
Exactly. All about energy and how it changes form.
Okay, what's next?
Then we've got a big section on wave and optics.
So sound waves, light waves.
Everything from the sound you hear to the light you see. Yeah. And after that, electricity and magnetism.
Which is, I mean, everywhere in modern life.
Absolutely powers so much. And then finally, it touches on modern physics.
Modern physics.
Yeah.
Like atoms and quantum stuff.
Precisely, delving into that fascinating smaller scale.
Wow, okay.
And within those big units, you've got specific chapters. Like in mechanics, there's rotational dynamics.
Spinning things.
Yeah.
Like tops or wheels.
Yep. And fluid statics.
Why boats float.
Or why some things sink. Then later, wave motion, interference.
Interference, where waves mess with each other.
Yeah, sometimes canceling out. Then you have electrical circuits, electromagnetic induction.
How we generate electricity.
That's a key part of it. And in modern physics, chapters like electrons, radioactivity, it's quite a range.
It really is. So where should we start our dive? Given those opening questions about, everyday stuff.
Good point.
Maybe start with some of those basic mechanics concepts. Chapter 1 looks like it covers surface tension, viscosity.
Sounds like a plan.
Surface tension. I always picture those perfect little dewdrops on a leaf. Is that it?
That's a classic example, yeah. Surface tension is defined as this force acting on the surface of a liquid.
Okay.
And it tends to make the surface area as small as possible.
Right, like it's pulling itself together.
Exactly. It's all down to the forces between the liquid molecules. Inside the liquid, a molecule is pulled equally every which way by its neighbors.
Okay, balanced out.
But right at the surface, those molecules don't have neighbors above them, so there's a net inward pull.
Ah, pulling them down and sideways.
Right. And this creates a kind of skin on the surface trying to contract. And the smallest area for a given volume is a sphere.
Which is why droplets are spherical.
Precisely. The book even gives the formula T equals F over L. Surface tension is like the strength of that skin along a certain length. It's why those tiny water droplets try to be round. They're minimizing surface energy. Detergents actually work by breaking this down, letting water spread out more easily.
Okay, so that inward pull makes the droplets round. And what about the little bugs, the insects that can, walk on water? Same thing.
Yes, that's the surface skin again. The insect's weight is spread out just enough.
So it doesn't break through.
Exactly. It doesn't break the surface tension. It's like a very, very delicate trampoline.
Wow.
The book also mentions how you can carefully float a needle, even though steel's much denser than water.
Because the surface tension holds it up.
The surface tension can support its weight, yeah.
Okay, surface tension. A liquid's strong, tight surface. Got it. Now, what about viscosity? That sounds like thickness, right? Like honey versus water.
Spot on. Viscosity is just a measure of how much a fluid resists flowing. It's basically internal friction.
Internal friction, yeah.
High viscosity, like honey or molasses, flows slowly. Low viscosity, like water, flows easily.
Makes sense.
And this friction comes from the molecules interacting as they slide past each other. What's interesting, though, is temperature.
Oh, yeah. How does that affect it?
Well, for most liquids, viscosity goes down as temperature goes up. Think about warming honey, it gets runnier.
Yeah, definitely easier to pour.
But for gases, it's actually the opposite. Viscosity increases with temperature.
Really? Why is that?
Because the gas molecules move faster at higher temperatures, so they collide more often, creating more resistance to overall flow.
Ah, never thought about that.
It's super important for things like engine oil. You need it to work properly whether the engine is cold or hot.
Right, needs the right viscosity across a range of temps.
Okay, so if viscosity is resistance to flow, what happens when you drop something into, say, that thick honey?
Ah, good question. That brings us to terminal velocity.
Okay.
When an object falls through a fluid, air, water, honey, whatever gravity pulls it down, obviously,
Right.
but the fluid pushes back up with a drag force, which is related to viscosity.
Okay, like friction from the fluid.
Exactly. Initially, the object accelerates, speeds up, but as it goes faster, that drag force gets stronger.
Ah, the faster it goes, the more the fluid pushes back.
Right. And eventually, the upward drag force perfectly balances the downward force of gravity plus any buoyancy.
And then
Then the net force is zero, and the object stops accelerating. It just keeps falling at a constant speed.
that's terminal velocity.
That's terminal velocity. So higher viscosity means more drag, which means a lower terminal velocity.
So things fall slower in thicker fluids, like
Yeah.
a feather versus a rock in air. Perfect example. The feather has huge air resistance compared to its weight, so it reaches its slow terminal velocity really quickly. The rock, much less so.
Okay, the fluid puts a speed limit on falling things.
Yeah.
Makes sense. Now, moving on to mechanics, projectile motion, basketballs, cannons.
Fireworks, yeah. Anything launched into the air.
What's the key physics idea there?
Well, assuming we ignore air resistance for simplicity.
Okay, ideal physics world.
Right. The only force acting is gravity pulling straight down. The big insight is that the horizontal motion and the vertical motion are totally independent.
Independent, how so?
Your horizontal speed, how fast it's moving sideways, stays constant. Gravity only affects the vertical speed, making it accelerate downwards.
Huh. So pushing something sideways doesn't change how fast gravity pulls it down.
Nope. Which is why, famously, a bullet fired horizontally from a gun hits the ground at the same time as a bullet simply dropped from the same height.
That's still kind of mind-bending, but okay, I see. And the path is usually that arc shape.
A parabola, yes. And how far it goes, how high it goes, how long it's in the air, that all depends on the initial speed and the angle you launch it at.
Right, the launch angle is key. Okay, what about things that spin? Rotational motion sounds like it covers that. Gyroscopes and stuff.
Exactly. Rotational motion is all about how things move around an axis.
Yep.
And you have rotational versions of familiar concepts.
Like speed and acceleration.
Yep. You have angular velocity, how fast it's spinning, and angular acceleration, how quickly that spin is changing.
Okay.
Then there's torque. That's the rotational equivalent of force. It's the twist or push that causes something to change its rotation.
Like using a wrench to turn a bolt.
Perfect. And the rotational equivalent of mass is called moment of inertia.
Moment of inertia. Okay, what's that?
It measures how resistant an object is to changes in its rotation. It depends not just on the mass, but how that mass is distributed relative to the axis.
Ah, like the figure skater example.
Exactly. When the skater pulls their arms in, they decrease their moment of inertia.
So they spin faster.
Right, because the same internal torque produces a bigger angular acceleration. There's a direct link, like F-ma, for linear motion.
So mass spread further out means more resistance to spinning.
Yep, larger moment of inertia, harder to speed up, harder to slow down.
That skater analogy really helps.
Okay.
And then there's simple harmonic motion, SHM. Sounds peaceful.
It can be. SHM is a specific kind of back and forth periodic motion.
Like a pendulum.
A pendulum swinging with a small angle is a great example. Or a mass bouncing on a spring.
Okay, what makes it simple harmonic?
The key is the restoring force. The force pulling the object back towards its middle equilibrium position is directly proportional to how far away it is from that position. The further you pull it, the stronger it pulls back.
Ah, okay. Like a spring stretches more, it pulls back harder.
Exactly. And this leads to that smooth, regular oscillation. We describe it using its amplitude.
How far it swings.
Max displacement, yeah. It's period.
Time for one full swing.
Uh-huh. And its frequency?
How many swings per second?
Right. You find SHM all over the place. From clocks to atoms vibrating.
Okay, that regular back and forth driven by that proportional restoring force. Right. Let's shift gears a bit. Heat and thermodynamics.
Sounds good.
The first law of thermodynamics sounds pretty important. What's the core idea?
It really is fundamental. It's basically the law of conservation of energy just applied to systems involving heat and work.
Okay, Energy can't be created or destroyed.
Exactly. It says the change in a system's internal energy, sort of the energy stored inside it,
Okay.
equals the heat you add to the system minus the work the system does on its surroundings.
So E equals QW. I think I remember that.
That's the one. Energy just gets moved around or changes form, heat, work, internal energy, but the total amount stays constant.
So if you heat up gas in a cylinder and it pushes a piston.
The heat you added, Q, increases its internal energy, but then the gas doing work pushing the piston uses up some of that energy.
Right. Makes sense. The book probably talks about specific processes too.
Yeah, like adiabatic processes where no heat is exchanged, or isothermal, where the temperature stays constant.
Okay, so energy is conserved. What about the second law of thermodynamics? That one always feels a bit more
That
abstract.
stuff, it is a bit deeper, yeah. It introduces the concept of entropy.
Entropy, disorder, randomness.
That's a good way to think about it, yeah. A measure of the disorder in a system. The second law basically says that for any isolated system, the total entropy can only increase over time or stay the same in ideal cases. It never decreases on its own.
Things naturally get more disordered.
In an isolated system, yes. A key consequence is that heat always flows spontaneously from hotter things to colder things.
Never the other way around.
Never spontaneously. You need to do work to make heat flow from cold to hot, like in a refrigerator.
Oh, okay.
The second law also puts limits on things like engines. You can't build a heat engine that's 100% efficient at converting heat into useful work,
Why not?
because some energy always has to be dumped as waste heat to a colder reservoir, increasing the overall entropy, the disorder of the universe.
So there's a fundamental inefficiency built into energy conversion and a direction to time almost. Things tend towards disorder.
That's a profound implication, yes. Okay, shall we move into waves and optics?
Let's do it. Starting with basic wave motion. What are the main kinds of waves?
Well, Chapter 7 probably makes the key distinction between transverse and longitudinal waves.
Okay, what's the difference?
Think about shaking a rope up and down. The wave travels along the rope horizontally, right?
Yeah.
But the rope itself moves vertically up and down, perpendicular to the wave's direction. That's a transverse wave.
Okay, oscillations perpendicular to travel, like light waves.
Exactly. Light is transverse. Now think about sound. A speaker vibrates back and forth.
Pushing the air.
Right, compressing and expanding the air in the same direction the sound is traveling. The oscillations are parallel to the wave's direction. That's a longitudinal wave.
Got it. Transverse is side to side. Longitudinal is push-pull. And they have properties like wavelength and frequency.
Absolutely. For any periodic wave, its speed, v, is just its frequency. F waves per second times its wavelength, distance between peaks. V is okay.
Simple enough. Okay. The book also mentions sound waves in pipes, like organ pipes or flutes.
Precisely. When sound waves get trapped inside a pipe, they can interfere with their reflections.
Bouncing off the ends.
Yeah, and they can set up standing waves. These are patterns where the wave doesn't look like it's traveling, just oscillating in place with fixed points of no vibration, called nodes, and points of maximum vibration, called antinodes.
Okay. Standing waves. How does the pipe affect them?
It depends if the pipe is open at both ends or closed at one end.
Ah.
In a pipe open at both ends, the ends have to be antinodes, maximum vibration. This means the pipe length has to fit multiples of half a wavelength. You get a fundamental frequency, and then all the integer multiples the harmonics.
Like 1 times, 2 times, 3 times the fundamental frequency.
Exactly. But in a pipe closed at one end, the closed end must be a node, no vibration, and the open end is an antinode.
Okay. Different boundary conditions.
Right. And this means the pipe length has to fit odd multiples of a quarter wavelength. So you get the fundamental, but then only the odd harmonics 3 times, 5 times, 7 times.
No even harmonics.
Nope. And the mix and strength of these harmonics are what give different instruments their unique sound, their timbre, even playing the same note.
Ah, so that's why a flute sounds different from a clarinet playing the same C. It's the harmonics. Fascinating. Okay then, acoustic phenomena, echoes, reverberation.
Yeah, this section likely covers those common sound effects. An echo is just a reflected sound wave you hear distinctly after the original sound.
Because it traveled further, bounced back.
Right. There's a noticeable delay. Reverberation is more like the persistence of sound in a room after the source stops.
Like in a big church or hall.
Exactly. It's caused by many, many overlapping reflections blending together.
Okay. And the Doppler effect, that's the ambulance siren thing, right?
That's the classic example. The Doppler effect is the change in the frequency and therefore pitch you perceive when the sound source and you are moving relative to each other.
Higher pitch when it comes towards you, lower when it goes away.
Precisely. As it approaches, the sound waves get bunched up, compressed, so the frequency you hear is higher. As it moves away, the waves get stretched out, and the frequency you hear is lower.
Understanding the wave compression and stretching makes that so much clearer than just it changes pitch. Okay, let's switch to light. Nature and propagation of light. Still waves.
Very much so, at least in classical optics. This chapter probably introduces Huygens' principle.
Huygens. How does that work?
It's a way to visualize how waves spread out. Imagine every single point on a wavefront.
A wavefront being like, the crest of the wave.
Sort of, yeah. A surface where the wave is all in the same phase. Huygens said each point on that wavefront acts like a tiny new source, sending out secondary spherical wavelets.
Okay.
And the new position of the wavefront a moment later is just the surface that touches all those little expanding wavelets.
Like drawing a line connecting the edges of ripples from lots of little points.
Exactly. It sounds a bit abstract, but it's a powerful way to explain how light travels, reflects, and even bends.
Okay. Light as expanding ripples made of tinier ripples.
Mm-hmm.
Got it. So what happens when light hits something? Reflection and refraction.
That's where Huygens' principle can be applied. Reflection is just light bouncing off a surface.
Like a mirror.
Right. And the law of reflection is simple. The angle it comes in at equals the angle it bounces off at.
Angle of incidence equals angle of reflection. Measured from.
Measured from a line perpendicular to the surface, the normal.
Okay. And refraction. That's bending, right? Like a straw in a glass of water looking bent.
Exactly. Refraction is the bending of light when it goes from one transparent material into another, say air into water or air into glass.
Why does it bend?
Because light travels at different speeds in different materials. It slows down in denser materials like water or glass. Snell's law is the formula that relates the angles and the speeds, or more commonly, the refractive indices of the materials.
Refractive index. A measure of how much it slows down light.
Pretty much. And a really cool consequence of refraction is total internal reflection.
Total internal reflection.
Yeah, if light is traveling from a denser medium to a less dense one, like from water trying to get out into air,
Okay.
and it hits the surface boundary at a shallow enough angle or large enough angle relative to the normal,
Yeah.
it can't actually get out. All of it gets reflected back inside the denser medium.
Wow. Like it's trapped.
Exactly. That's the principle behind fiber optic cables. Light signals bounce internally along the cable for huge distances with very little loss.
Amazing. So light gets guided by bouncing inside the cable. Okay. Interference. This sounds like light waves interacting again.
It is. Interference happens when two or more light waves overlap in the same space.
Okay.
We use the principle of superposition. It just says that where the waves meet, the resulting wave is the sum of the individual waves.
So they add up.
They add up. If the crest of one wave meets the crest of another, they add together to make a bigger crest, brighter light. That's constructive interference.
Makes sense.
But if the crest of one wave meets the trough of another, they can cancel each other out. That's destructive interference resulting in darkness.
Light plus light can equal darkness.
It can. The classic demonstration is Young's double slit experiment. Shine light through two tiny, close slits.
Yeah.
And on a screen behind them, you don't just see two bright lines. You see a whole pattern of alternating bright and dark bands or fringes.
Because of constructive and destructive interference from the light waves spreading from each slit.
Exactly. It was incredibly strong evidence that light behaves like a wave.
That is still mind-blowing. Okay, what about diffraction? Bending around corners.
Diffraction is pretty much that, yeah.
Yeah.
The tendency of waves to spread out when they pass through narrow openings or bend around obstacles.
Does light do that noticeably?
It does, but because light's wavelength is so incredibly small, you usually only see significant diffraction when the opening or obstacle is also very small, like comparable to the wavelength.
Ah, okay. So it's not like sound bending around a corner, which is much more obvious.
Right. Sound has much longer wavelengths. Diffraction causes light to spread out from sharp edges or narrow slits, creating patterns. It's also what fundamentally limits how sharp an image you can form with a lens or see with your eye. Diffraction sets a limit.
So even light doesn't always travel in perfectly straight lines. It can spread. Good to know. Okay, last one in this section. Polarization. What's going on there?
Polarization is specifically a property of transverse waves, which, as we said, includes light.
Okay, so not sound waves.
Right, longitudinal wave can't be polarized.
Yeah.
Polarization describes the direction of the wave's oscillations. For light, it's the direction the electric field is vibrating.
Light has an electric field.
It's an electromagnetic wave, so it has both oscillating electric and magnetic fields perpendicular to each other and to the direction of travel.
Okay.
In normal, unpolarized light, say from the sun or a light bulb, the electric field vibrates in all directions perpendicular to the travel direction. It's random.
Okay.
Polarized light has those vibrations restricted to just one plane.
How do you do that?
You use a polarizing filter. Think of it like passing a rope wave through a picket fence, only the vibrations aligned with the slats get through. Polarized sunglasses use this to block reflected glare because glare is often horizontally polarized.
Ah, so the filter blocks the horizontal vibrations.
Exactly. And the fact that light can be polarized is definitive proof that it's a transverse wave.
Fascinating. Tells us about the wave's orientation. Okay, huge section. Wave and optics. Let's tackle electricity and magnetism. Electrical circuits first.
Makes sense. The foundation. This chapter would introduce the basic components.
Resistors, capacitors,
Yeah.
inductors.
Those are the main passive ones, yeah. Resistors impede current flow. Capacitors store energy in an electric field. Inductors store energy in a magnetic field and resist changes in current.
Okay, and the main rules, Ohm's law.
Definitely Ohm's law. V equals IR. Voltage equals current times resistance.
Yeah.
Relates the electrical pressure, voltage, the flow current, and the opposition resistance.
And Kirchhoff's laws. Learn those names.
Crucial for analyzing circuits. Kirchhoff's current law, KCL, says the total current flowing into any point or junction in a circuit must equal the total current flowing out. Like water in pipes, it doesn't just disappear.
Conservation of charge. Makes sense.
And Kirchhoff's voltage law, KVL, says that if you go all the way around any closed loop in a circuit, the sum of all the voltage rises, like from batteries, and voltage drops across resistors must be zero.
Conservation of energy.
Exactly. These two laws are the essential tools for figuring out what's happening in almost any circuit.
Okay, Ohm and Kirchhoff, the building blocks for circuit analysis. Now this next one sounds cool. Thermoelectric effect. Heat and electricity.
Yeah, it's about the direct link, the conversion between thermal energy and electrical energy. Two main effects here.
Okay.
The Seebeck effect is where if you join two different metals or semiconductors together and keep the junctions at different temperatures.
Like one hot, one cold.
Yeah, a voltage difference appears across the junctions. You can generate electricity directly from heat. And the Peltier effect is kind of the reverse. You pass an electric current through a junction of two different materials.
Yeah.
And it causes heat to be either absorbed or released at that junction. It can act like a heat pump.
So you can use electricity to create heating or cooling without moving parts.
Exactly. Thermoelectric coolers, their techs, use the Peltier effect. And the Seebeck effect is used in things like thermocouples for measuring temperature and potentially for generating power from waste heat.
Very clever stuff. Okay, next. Magnetic field. What exactly is a magnetic field?
Fundamentally, it's a field of force produced by moving electric charges or by intrinsic magnetic moments of elementary particles like electrons.
Okay, so moving electricity creates magnetism.
That's a huge part of it, yes. The book probably talks about the force this field exerts on other moving charges, the Lorentz force.
Right.
And the direction of that force is kind of tricky. It's perpendicular to both the charge's velocity and the magnetic field direction. Uses the right-hand rule, usually.
Ah, yes. I remember the hand gymnastics for that.
Yeah. It also covers how currents create fields. A straight wire makes circular field lines around it. A coil of wire, a solenoid, makes a strong, fairly uniform field inside, much like a bar magnet.
So electricity makes magnetism. Does magnetism make electricity? Electromagnetic induction?
Exactly. That's the flip side, and it's incredibly important, discovered by Faraday.
Faraday's law.
Right. It states that if you change the magnetic field passing through a loop of wire,
Change it how? Stronger, weaker, moving it.
any change in the amount of field passing through the loop, what we call magnetic flux, if that flux changes, a voltage, an electromotive force, or EMF is induced in the loop.
And that voltage can drive a current.
If the loop is closed, yes. This is how almost all our electricity is generated. Generators spin coils of wire in magnetic fields, or spin magnets near coils of wire. The changing magnetic flux induces an EMF.
Wow. So simple a principle, but powers the world. And Lenz's law. What's that?
Lenz's law just tells you the direction of the induced current. It says the induced current will flow in such a direction that the magnetic field it creates opposes the original change in flux that caused it.
Opposes the change, like inertia. Resists the change.
That's a good analogy, yeah. Nature resists the change in magnetic flux. This is also key for transformers, using changing magnetic fields in one coil to induce voltage in another, stepping voltage up or down.
Faraday and Lenz. Absolutely crucial. Okay, the book also covers alternating current, AC. That's our wall sockets, right?
Yes, AC is where the current direction periodically reverses, back and forth, back and forth. Unlike DC, direct current from a battery, which flows one way.
Why do we use AC?
The main reason is that it's very easy to change the voltage of AC using transformers. You can generate power, step the voltage way up for efficient long-distance transmission with low current, then step it back down near homes and businesses to safer levels. Much harder to do that with DC.
Ah, transformers are key. So AC has voltage and current going up and down.
Yeah, usually sinusoidally. We talk about its frequency, how many cycles per second, like 50 or 60 hertz, and RMS values.
RMS, root mean square.
Yeah, it's a kind of average value. The RMS voltage or current gives you the equivalent DC value that would deliver the same amount of power.
Okay, and I see the term impedance here. Is that like resistance for AC?
It's the overall opposition to current flow in an AC circuit, yes. But it's more complex than just resistance because capacitors and inductors behave differently with AC. Their opposition depends on the AC frequency. Impedance combines resistance and this frequency-dependent opposition called reactance from capacitors and inductors.
So impedance takes into account all three components, R, L, and C. Got it. Okay, final big section, modern physics. Starting with electrons, what's key here?
Well, understanding the electron itself is a fundamental particle. It's negative charge, it's tiny mass. The chapter might also cover how electrons get kicked out of materials.
Like thermionic emission,
Yeah.
heating things up.
Yeah, or the photoelectric effect light shining on a surface knocks electrons out. Or applying a strong electric field. Knowing about electrons was essential for, well, all of electronics.
The little charge carriers.
Yeah.
Okay. Then photons, light again, but as particles.
Exactly. This is where wave-particle duality really comes in. The idea largely from Einstein explaining that photoelectric effect.
Which waves couldn't explain properly.
Right. He proposed that light energy doesn't come in continuous waves, but in discrete packets or quanta, called photons.
Little bundles of light energy.
Yep. And the energy of each photon is directly proportional to the frequency of the light. E equals hf, where h is Planck's constant.
So light is both a wave and a particle.
Depending on how you look at it.
That's the weird and wonderful core idea of quantum mechanics, yes. Sometimes it acts like one, sometimes the other.
Okay, still processing that one. Next, semiconductor devices. This is computers, phones.
The absolute foundation of them. Semiconductors are materials like silicon, whose ability to conduct electricity is somewhere between a conductor like copper and an insulator like glass.
Okay.
But the magic happens when you dope them. Add tiny impurities to create either N-type semiconductors with extra free electrons,
Positive or negative?
or P-type with holes where electrons are missing, which act like positive charge carriers.
P for positive.
Right. And when you join a piece of P-type and a piece of N-type material together, you get a PN junction.
And that junction is special.
Very. It forms the basis of diodes, which let current flow easily one way but block it the other way, and transistors, which can act like tiny electronic switches or amplify signals.
And millions or billions of those make up computer chips.
Essentially, yes. These simple building blocks enable all our complex electronics.
Incredible. What about quantization of energy? Energy comes in packets, too.
At the atomic level, yes. Just like light energy comes in photons, the energy within atoms is also quantized.
Meaning?
Meaning electrons orbiting an atom can't just have any old energy. They can only exist in specific, discrete energy levels or states. Like they can only stand on certain rungs of an energy ladder, not in between the rungs.
Ah, okay. Specific allowed energies.
Right. This was Niels Bohr's big idea for the hydrogen atom. To jump from one level to another, an electron has to absorb or emit a photon with exactly the right amount of energy, the difference between the levels.
That's why atoms emit specific colors of light. Those colors correspond to the energy differences.
Precisely. It explained atomic spectra perfectly. Quantization is fundamental to how atoms work.
Okay, energy isn't continuous down at that level. Finally, radioactivity. What's the core idea?
Radioactivity is the spontaneous process where unstable atomic nuclei decay or break down to become more stable.
Unstable nuclei. Too many protons or neutrons.
Often, yeah, an imbalance. And when they decay, they release energy and particles.
Like alpha, beta, gamma.
Those are the main types mentioned here, yes. Alpha decay is when a nucleus spits out an alpha particle, basically a helium nucleus, 2 protons, 2 neutrons.
Yeah, okay.
Beta decay usually involves a neutron changing into a proton and emitting an electron, or a proton changing into a neutron and emitting a positron. Changes the element.
And gamma. Gamma decay is when an excited nucleus releases excess energy as a high-energy photon, a gamma ray, without changing its particle composition, just settling down.
Okay. Different ways unstable atoms release energy and transform.
Yep. And this has uses from medicine to dating ancient artifacts to nuclear power.
Wow. We have really flown through an entire year of physics.
We really have.
Okay.
It's amazing how broad grade 12 physics is, covering everything from basic mechanics up to the quantum world.
Yeah, even this quick tour, without the math, really gives you a solid framework for understanding so much.
It connects the dots between everyday phenomena and the underlying principles.
Absolutely. For me, just revisiting surface tension, why droplets are round, understanding that molecular pull and energy minimization,
Yeah.
that clicked again.
Yeah.
And the light interference thing, light plus light making dark, is still just wild.
It is pretty counterintuitive, and hopefully for you listening, seeing these connections helps you appreciate how things work, whether it's a simple straw or your complex smartphone.
Yeah. It definitely sparks curiosity, right? Makes you look at the world a bit differently.
Hopefully.
So, as a final thought, think about how all these different areas we touched on, mechanics, waves, E&M, modern physics, seem separate, but they're all linked by these fundamental laws.
They really are deeply interconnected.
What other connections might be hiding in plain sight? Maybe in the things you see or do every day. Something to ponder.
A great question. And if any specific topic really grabbed your interest today, maybe dive a bit deeper into that one yourself.
Definitely. Well, thanks for joining us on this deep dive into the world of grade 12 physics.
Been a pleasure.
Until our next exploration, keep wondering.